So this precept will cover red-black trees and hashing and algorithm design. Let's take the first question, which deals with binary search trees. So red-black trees are kind of a binary search tree, except it is balanced. So the question here is that we want to label each node in the following binary tree with numbers from the set, so that it's a legal binary search tree. Now, the best way to think about this problem is that given a shape of a BST, where do we place the given keys? There are many ways to think about this. One way is to say, what is the smallest key? In this case, 2, and where we place the smallest key, which we place at the leftmost node. You can also think about what's the largest key. In this case, the largest key is 42. We place at the rightmost node. So in other words, if you take the list of numbers given and sort it and then do in-order traversal and place them in the order, you would get the in-order traversal in this order here. So that's the shape of the tree and where we place the elements. So let's take a look at the second part. If it's a red-black tree, we ask in the question which ones are red and which ones are black. Now, to understand that, let's think about a legal left-leaning red-black tree. The invariants are no node has 2 red links connected to it. Every path from root to null link has the same number of black links, and red links lean left. Therefore, all the black links must be leaning right. So the key idea here is, let me take a black here, so we know that this has to be black and this has to be black. The other ones can be red or black. But how do we determine the other ones? So the one way to think about that is, you draw all the null links, and we know that the number of every path from root to the null link. So for example, if you take this path 1, 2, there are 2 links in that path. Therefore, if you take the path from here to here, null links are always black. You can only have 2 links, and therefore this link has to be red. Let's make the same argument here. If you look at the number of links from root to here, there are 2 black links already, and therefore this has to be a red link. Let's make the same argument here. Number of links from here to here should be the same. We can only have 2 black links, and therefore these 2 are the black links, and therefore this must be red. If you look at this one, now we have 2 black links and 2 black links, 2 links here, 2 links here, and 2 links here, and 2 here, 2 here, and 2 here. So we have a valid red-black tree, left-leaning red-black tree. Now, the way we thought about this problem is that by looking at this, you can convince yourself that it's not possible to assign any other order into this tree. So second question is about the hash tables. The question is, if the hash table size, let's take a pen here, is greater than or equal to the number of keys. So we have, suppose the table size is n, number of keys is m. We are saying that m is less than or equal to n. The linear probing hash tables are designed such that they are at least as big as the number of keys, because you need to find a place for each key. And therefore we can only have less than or equal to the table size. So if the table is size n, we can only have m keys that's less than or equal to n. So the key thing about the linear probing is that suppose you try to hash into this place and it's occupied, it's occupied. You keep going, but it's guaranteed because m is less than or equal to n, you're always going to find a spot. So the answer to this question is yes. Choosing a hash function. A bad hash function is something that causes a lot of problems. For example, the worst hash function is h of s equals a constant. All keys will hash to the same bucket if that's the case. Another bad hash function is going to be h of s equals the sum of the characters. Now this will cause all permutations of a string to hash to the same place. Any bad hash function can cause too many collisions. For example, if your function is a constant function, every key will collide with another key. And if your function is something like this, then every permutation of the string s will collide with a different permutation of the same string. So there'll be many collisions. Because there are many collisions, you're going to have some performance degrade because you will have to continue to look for places to insert. Even if it's a separate chaining table, the chains can become very, very long. No constant time guarantee. The whole idea of a hash table is constant time guarantee. If there are a lot of collisions, we may end up with a very long chains. For example, we may have a chain of length n over 2. That can be very bad. So think about a function that just takes the mod 2. So all hash codes are going to be either 1 or 0. So in this case, every chain, all the chains are going to be n over 2. There will be 2 long chains. Too much clustering if you use linear probing. So one of the problems of collision is that when you collide, you keep looking for it, and you keep looking for it, and then you find the next place and place the element there. This creates a big problem. So clustering is when many keys starting to saturate in a specific location. This causes more and more keys to crowd that place. It's like a traffic jam. One or two things can cause a jam, and all cars that follows joins this jam. So the clustering is a big problem in linear probing when you're using a bad hash function. The third question says, if a linear probing hash table is 50% full, the average number is 1.5. This follows from a formula that we have seen in the book or lecture notes. If alpha is 0.5 or 50% full, alpha is the load factor. We can just substitute alpha equals 0.5 here and find the answer is going to be 3 over 2. That's going to be... Alright, so the next question is about whether the searching in a hash table is always faster than searching in an LLRB. We know that we have a log n search capability in balanced binary search tree, red-black tree. And the hash tables are generally fast, so this can be constant time. But the problem is if you have a bad hash function, that can be very bad. So I think the answer to this question is it's not always faster. So you should say no, unless we assume uniform hash condition. So if you assume a uniform hash condition, this means that all the keys are equally likely to be in any one place. This means that you have a better performance in the hash table and you have a constant time guarantee. And so unless we can assume the uniform hash function, the answer to this question is no. Now here's another question. It says that, is it possible to find a key with a maximum value in a hash table in worst case log n time? Now keep in mind that log n time means that you're not supposed to look at all the keys. But that's not possible if you have a hash table which is always unordered. So we have no idea where the max is. So this means that you have to look at all of them to figure out which one is the max. Right? So if you're looking for the key with the maximum value, you have to look at all of them. So this means it's going to take linear time. So the answer is no. So it's the same answer if someone asks you, can you find, will there be an algorithm? Will there be an algorithm that can find the max in less than linear time if we don't know anything about the data set? The answer is no, because if you don't know anything about the data set, you must look at all the data. That's going to take you linear time to do it, and therefore it's not possible. So those are the kind of things you need to understand at this point to that shows some deep understanding about the algorithms and possibilities. All right, so the next question is about if you have a linear probing hash table. So this means this is just like an array or something, right? That's the linear probing hash table. It says deleting many keys can degrade the performance. The answer is yes, because if you delete a lot of keys, in between, we leave some dummy things in there. So when you're looking for a key, you may start here, but you have to go over these deleted keys to get to here. So this means that it can degrade the performance. So this means that if there are a lot of dummy keys in the hash table, one possibility is to rehash and remove all the dummy keys and then start all over again. So that can be much better than just leaving a lot of dummy keys in there. Cache performance, yes. So linear probing is about accessing things. Like if you access as of I, then most likely you'll be accessing as of I plus 1 next. And this means that cache, the computer will bring those adjacent things from the memory to somewhere close to CPU so you can access them quickly. So the answer to this question is yes. But it's not always true if you have like a linear probing, the separate chaining hash table. So in this case, these are not adjacent. These are not adjacent to each other. They are just blocks of memory coming from a variety of places. So we don't have the same cache performance if you have a separate chaining hash table. Easy to implement, yes or no. I guess it depends whether you like linked list, which means that separate chaining, or you like arrays. All right. So the next question is it's a little bit interesting question. It says that we have some random strings of length 5. So this means that we have a string, we can say a string of character 0, character 1, character 2, character 3, character 4, and they're all coming from the ASCII table. So this means that the S of I, any character value is between 127, this is the largest value in the ASCII table, between 127 and let's say 0. You can say 32, but let's say 0, that's fine. And so if you add them up, if you add 5 of those things, if you add from I equals 0 to 4, so this means that each one has a max value of 127. So the 5 of them has a max value of 127 times 5. And the mean value of 0, 0 times 5. So this turns out to be about 635. So how does this work? So you have a 10 we are doing into a separate chaining hash table. So we have 10,000 locations starting from 0 to 9999. And then what we are trying to say is that every hash code is going to be between 0 and 635. So you're only using 636 locations, and these things will be filled, and the rest is not. There are 10,000 things in here, and all of these chains are going to be null chains. There's nothing coming out of them. And so this means that you're spreading 10,000 things because it's random. You assume that you're spreading 10,000 keys over 636 places, and that's roughly about 16, 17. So you have the average chain length of 16, which is just too much for a hash table. We expect about average chain length of about 4, and so on. All right, so the next question is an algorithm design question, the kind of question you will get in the midterm. It gives you some conditions and it says, okay, find an efficient algorithm. It says that the B, this is the array B, is a shift you have an array A which is sorted, and if you rotate the array A sorted, you get this. In other words, in this case, we have sorted the array A by 3 positions, and so the largest 3 elements came to the left-hand side, 34, 55, 89. And so you're looking for this minimum element. So the problem says that find an efficient algorithm. Now, it couldn't be big O of n. That's not possible, because this means that anyone can find the minimum element if you are allowed to do n operations. You just go through the array and find it. So you have to do better than n. So this means that it has to be maybe log n or better. Now, it's a good log n algorithm because we know that we have binary search, which is log n algorithm. So binary search. We can do binary search, and it's perfect for the binary search because we have some sorted arrays. The only problem is this is not like a continuous sorted array. So you have a sort of a sorted array that are increasing, and then suddenly drops to 1 and then start to increase again. So you have like two sorted arrays, really. I mean, you have this sorted array and this sorted array. All right, so you're trying to use some level of binary search to find this position R. So the question reduces to the following. You want to find R such that B of R is less than B of R minus 1. So this means the one before that is bigger. So that's the place that it actually changed from increasing to a smaller value. So you want to find this. Now, obviously, this is our test conditions. Now, in binary search, typically you're looking for a key. Now, here also you're looking for a key, but you're looking for a condition. You're looking for the only place in the array that satisfies this condition. But there's an edge case that you have to consider. So you have to say, if R equals 0, this means that I cannot compute this, because that would go array index out of bounds. So R equals 0 means that you haven't shifted at all. So how do we know that? So R is 0 if you take the B of low, so assume that this is low and this is high. So if B of low is less than B of high, that means we haven't shifted at all. Otherwise, B of low is always going to be greater than B of high if you have shifted a little bit, right? So just check that condition, and if that condition is true, you're done. R equals 0, you can return that. Now, if that's not the case, then we should think about the following. Suppose we look at the B of mid. So compute the mid. This is what we do with a binary search type of an algorithm. So take the B of mid. Suppose B of mid is less than B of high. So if B of mid is less than B of high, this means that your element R should be to the left of you, because you have a sort of an increasing sequence of things in here. So this means that you want to kind of look at the left-hand side of the array, and then you set the high to mid and continue, high to mid and continue this process. And then you keep the low the same, and you kind of want to look at the left-hand side of the array. Suppose B of mid is greater than B of high. So suppose B of mid is greater than B of high. So you're in a situation like this. Maybe this is your mid at some point. And that B of mid happens to be greater than B of high. So this means that it should be somewhere to the right of B of mid. So in fact, you can set the low. Now you want to move to the low to mid plus 1, and you can start from there. Now, you will stop this process when the low and the high are going to be just an array, When you get to an array of size 2, you're just looking at this array to find this element. And when you get to this location, this B of R must be less than B of R minus 1. So that's the condition that you're looking for. You will probably get to an array of size 2, and you can stop that. So as you can understand, this can be done in log n time because it's just a binary search that you have to do. The second part of this is that once you identify what the R is, then you have two arrays. One from the array from R, the index R, to n minus 1, and the array from index 0 to R minus 1. So this side of the array and this side of the array. So if you're given a key K, you can say, let's take a look at K and compare that to the A's of n minus 1. So if you compare K to A's of n minus, or B's of n minus 1 in this case, so if you compare to this, and if it's less than that, so it should be here, because it couldn't be on this side, because everything on this side is greater than B of n minus 1. So then you search in this case the array from R to n minus 1. If K is bigger than or equal to say B of low, okay, B of low, in this case B of 0, then you want to search the array segment from 0 to R minus 1. So it's a binary search. So either binary search a sorted array here or sorted array here. Now they are both completely sorted, these segments. So you'll be doing log n things, and so altogether you can be doing 2 log n operations to do it. So these are the kind of questions that you have to do in the midterm, but the key thing here is that don't write too much. Don't write Java code. Just write an argument very clearly. This is what the steps are. and just describe it, and don't write too much. Don't contradict yourself. Just keep it very brief. We're always looking for a few lines of descriptions. You don't really need a lot of lines of description for solving these problems. You can get full credit to a partial credit by doing just enough. Also, don't give two solutions. If you give two solutions, you may end up with a grade for the lowest graded solution. So just be confident about one solution and just provide a clear description of that solution.